In this video, we're going to introduce Euler's method, which is an extension of the slope field visual technique to something that's more quantitative. The premise is straightforward. Like in a slope field, if you're given a point, you know that by being given the differential equation dy dx equals something, you can compute the slope. And if you can compute the slope, then Euler's method says, well, let's follow that slope. Let's pretend the function is constant on a small interval. And this is exactly what we did back with original work on integration, other fields. We assume that things are constant over a small interval, and then following a tangent line or a straight line with that slope, we end up with a new location. Then what we can do is go back to our formula, get a new slope. Maybe it's a bit steeper now. And once we had that new slope, we follow it for a while, end up at a new point, find our slope. And once we have that new slope, maybe it's flattening out again. We follow that for a while. And what we end up with is a straight line approximation of little segments that should be a good approximation to the actual curve, which is the continuous solution we'd like to have if we had our druthers. We would use this as a fallback if we somehow, or for some reason, can't get an exact solution. Here's the algorithm of the process. We have a starting point, we compute the slope, and then we follow the slope for one step, delta x. Again, a common theme. Start here, and then we fix the step size from left to right. The interesting part, or the new part, is how we would compute the vertical distance. How do we know where we are here? Well, if we know what delta x is, and we know what the slope is, we know that the slope is the change in y over the change in x, but we want to know the change in y. Well, that's going to be our slope, bring the delta x up, times delta x. So there's nothing deep going on mathematically here. It's just interpreting again this dy dx as a slope and using that as a construction tool to help us build this straight line segment. To formalize the new and old positions, we start with our current x and we add delta x to it. That's all that happens in the horizontal direction. The y direction is a little more complicated, but it's just capturing this idea. We have our old y plus the slope times delta x. Why do we do that as a change? Well, because that equals delta y for any straight line. Let's apply that approach to a specific differential equation, dy dx equals x plus y. So again, we can think of this now as a formula for slopes. And once we have that formula for slopes, if we know where we're starting, here we're starting at x equals 0, y equals 0.1. We can calculate the slope there as 0 plus 0.1. So we have a shallow slope. And then we combine the slope, the 0.1, with the delta x, which is our step size given to us in this problem. We're going to take a step to the right of 0.1. And we can find out that we don't actually go up that high. In fact, we go up by 0.01, which is the product of those two slope and delta x values. We take our y, we add the delta y we just computed, and we end up at 0.11. So we know exactly where we are at this new point after that one step. We do the same thing again. The slope at the point we're at now will be x plus y, 0.1 plus 0.11. That'll be 0.21. Then we want to find out from there. So the slope's a little steeper now. We're going to then compute from the slope and the step to the right the change in y that we're going to get. We're going to go up by a little bit here, following that slope line for one step. That becomes our delta y. We add that to where we were before, and we end up with 131. Again, just finding the change in x, that's always fixed. And finding the change in y is more complicated, but not much. And we're just adding that to the old y value to represent the old plus the change. We do this again. X plus y is what gives us our slope, 0.331 here. We then take our slope, multiply it by our step, and we get 0.331. Again, we take that as our delta y, we add it to this. Being careful with our decimal places, it's 0.0331 after we multiply here. And we end up with 0.164. And again, all we're capturing are these steps in the process. Take these two, find the slope value. We're going to get 0.464. We take our slope times delta x, and our delta x is consistently 0.1. We're always taking that same step to the right, 0.0464. We add that to what we have here, and we end up with 0.210, cutting it off a little bit. Our new slope is 0.610, and so on. What we do with that is we get a prediction of our position at different x values, filling out the graph here with straight line segments. Here's a picture of the scenario we're talking about. This is the slope field defined by x plus y. We can confirm that by looking, say, at x equals 1, y equals 0 here. We see a slope of 0 plus 1, which is 1, 45-degree slope. Then we go to our starting point, which was 0.1 in the y and 0 in x. Notice how small these steps are. When we follow them, we're going halfway along here to 0.1. We can go back to the table for a moment, and we get these values showing up. We would then plot them as almost the same thing, 0.11. 0.13 is still fairly low. 0.16 is about halfway up to the 0.2, and it happens here at our third step. And finally at 0.4, we're just above there, so it's probably more like that. And so what we've drawn here is a sequence of straight lines that approximate what we would have maybe sketched if we had been asked to draw this by hand. This is by hand, not very accurate, but has the clear flavor of the slopes that we're seeing on the field. This blue line is what we're getting more mechanically through this process that we call Euler's method, a much more strategic or numerically based strategy for drawing each of these line segments and trying to build up the solution with small segments that way, rather than trying to just eyeball it. So that's the process. Often we'll be asked, though, we know the straight line segment process is not going to be perfectly accurate. Why? Well, because as we would have moved from this point to that point, the curve would have changed, the slope would have changed. And the question is, or one question that arises, is how are we off? In what direction are we off? Let's make this more explicitly straight lines here, magnified for the purposes of being able to see any deviations. But as we do our curve, and as we look at these lines in the slope field, we see that things are curving up as we move to the right. And that makes sense. As x gets bigger and y get bigger, the slopes get steeper. So we have this concave up shape to our solution. And we've seen this kind of issue before, where if our solution is going to be concave up, but we are following it with Euler's method with the straight line approximation, we're going to end up consistently below the actual curve. And so in this scenario, Euler's method is predicting a little low, or is an underestimate. Not by much necessarily, because we're taking very small and careful steps, but it's still an underestimate of the actual solution. The actual solution being the red line that would bend up, would be concave up, and bend away just a little bit each time from the straight line approximation that we're using.